And it looks like we've started recording.
All right.
So take it away, Jared.
Cool. Hey, good evening, everybody. Um, Welcome to the March 2022 meeting of the Chicago Data Professionals User Group. I am going to talk tonight about Azure Synapse Analytics and specifically the dedicated SQL pool aspect of it. This is formerly known as Azure Data Warehouse. Um, and in some cases, it can be related almost directly to what was known as PDW or APS, which is still out there, but it's Microsoft's data warehouse appliance that also uses an MPP architecture. So what we're going to talk about tonight, we're going to focus on what that MPP architecture means. And some of this is going to tie back to another talk that I gave several months ago on column store indexes. I think I also gave it this last month to the Chicago Suburban user group. And I believe that they may have recorded it. I'm pretty sure that we recorded my talk on column store indexes. So that might be useful to go back to after this presentation. So a little bit about myself. Again, my name is Jared Karney. I'm a senior customer engineer at Microsoft. And all that means a customer engineer is I work with customers to help them unblock problems that are keeping them from progressing forward in their digital transformation. I also do a number of trainings, which I consider to help also unblock things. So I can be a problem solver, I can be an architect, I can be really an advisor. And so I work with customers of all different sizes, doing all sorts of different things with the Microsoft Data Platform, primarily now in Azure, but also spanning some other clouds and certainly still getting back to my roots of the SQL Server database engine. I am located here in Chicago. Well, I don't live in Chicago anymore. I just recently moved out to Glenview, which is why I have this beautiful background on my picture right now, because behind me are a whole bunch of boxes that have yet to be unpacked here in my basement. I'm going to go ahead and turn off my camera probably for the remainder of this meeting just to save on any bandwidth issues. So give me a moment, I'll shut that off. Cool. And so tonight, what I'd like to talk about are these four things and focus on these four things. SMP versus MPP. SMP being symmetrical multiprocessing, which is a typical SQL Server or virtual machine, versus MPP, which is what the Synapse SQL pool is. And specifically, this is a dedicated SQL pool that I'm talking about. We're going to talk about some of that architecture, specifically, again, for a dedicated SQL pool. We're going to talk about table geometries and indexes, which are really what set this apart in terms of design and understanding, and even how we look at our queries and query plans. And then we're going to talk about data movement. Data movement feeds upon the table geometries and indexes, or maybe I should say it builds upon that, not necessarily feeds on it. But it's important to understand those table geometries and indexes to then understand data movement, because when we performance tune in a dedicated SQL pool, we are oftentimes not looking at the same types of things that we look at in an SMP architecture, like what type of join is it doing, a hash or a nested loops? And am I getting a sort warning? Or am I doing a scan versus a seek? These aren't the ways that we look at performance tuning in general, and in most cases in a SQL pool, but we actually are looking at something called data movement and reducing it. So let's talk about SMP versus MPP. So to define this, symmetric multiprocessing is what we typically think of when we think of parallelism in a traditional relational database or just a regular, good old computer or server. Okay, so we have one or more CPUs to run these tasks, but they are sitting on the same motherboard, right? They're sharing the same OS. More importantly, they're sharing the same memory. the same IO, network, everything, right? They can split the work up into parallel threads by using cores and even hyper-threading, right? But at the end of the day, they are sharing everything else. They're part of one computer. They're part of one server. Okay. And so those are our traditional applications and database platforms, SMP architecture. MPP is quite different. So instead of having a single, let's say, node or computer that has multiple CPUs, we now have multiple servers or computers with multiple CPUs. And what we're doing there is we're separating out that bus. And by bus, I mean, the inputs and outputs from the CPU to disk and to network and to memory, right? We're separating these out. Some people kind of talk about this in many cases as like sharding. But the idea is that each individual compute node is not sharing resources with each other. In fact, it's known as shared nothing. And then each node is connected to each of the other nodes, typically through a control node. Not necessarily directly, although they are. But the control node actually sits on top and helps kind of orchestrate what's going on. I like to think about this as like the foreman in the factory kind of standing up on his platform in the corner and directing work to all the people that are down there below. Versus, let's say, SMP architecture is maybe more like a single worker, but they've got two different hands, right? And each hand has 5 fingers, but they're all sharing the same brain. And it's the same brain that's allowing the hands and fingers and muscles and everything to work together. But when I add a foreman and multiple individuals, that's when I get MPP architecture. Any questions about the difference between those two? Okay, so why, right? MPP, again, it stands for massively parallel processing. And similar to SMP, it's a divide and conquer strategy. Okay, but the difference here is that we're not sharing the memory. We're not sharing the disk IO. And part of this makes it a lot easier to scale up and out, right? In fact, the disks, the IO, aren't even located locally to the machine. They're remote storage, much like a SAN, right? But in the cloud, it's a storage account. They're remote disks. And we're going to see how that makes this really kind of pop and work the way that it does. Now, in order to do this, we do need that control node or something to schedule the different tasks, to divvy up the work appropriately. And as you're going to see in the next diagram, we're going to do that with a control node. All right, so another way of looking at this is you have one worker with 100 nails and a hammer. And one worker with 100 nails and a nail gun. And so you take 100 nails, let's say, and you divide them between 50 workers with a hammer. Right now you got 50 workers are driving 2 nails in parallel. But if you take 100 nails and divide them between 100 workers with a hammer, right? Then we put all 100 nails in at once instead of in 2 times the time. So the idea here is if we start to scale this up, we can really break out the amount of work. And it becomes almost limitless. Now, in a dedicated SQL pool, you'll see it's not limitless, but for all intents and purposes, for most people's needs, it kind of is. So let's take a look at our dedicated SQL pool specifically. The first thing we see up at the top is a control node. Okay. And that control node is where we are connecting to. It's where we're sending our queries through. Right? So that's kind of our endpoint. And when we issue our query, it does the work of figuring out how to split that query up into smaller jobs. When it does that, it sends that information out. It sends out its commands to all of the different compute nodes. Okay? And then they process the queries. It's pretty straightforward. What's interesting to note in a dedicated SQL pool is that we always have 60 distributions. So what does that mean? That means ultimately every single SQL pool, no matter how big you make it, no matter how you scale it, always has 60 Azure SQL databases, Azure SQL DBs. And those are located at the compute node layer. Okay. Now the options that you have, you could have a single compute node. It kind of defeats the whole idea of an MPP architecture, but you can do it. It's mainly for development purposes, kind of unit testing, certainly not performance benchmarking, because there's no reason to performance benchmark against a single node when you're going to have more than a single node. So you can't really do an apples to oranges. You can't say, well, my speeds are going to double when I have 2 nodes, because the MPP architecture is going to be a little bit different as soon as you get to 2. But the idea here is that each of these Azure SQL DBs each have their own memory, they each have their own storage, they each have their own network. And if I were to spin up a Synapse SQL pool with a single node, it would simply be like a SQL Server instance with 60 databases. 60 identical databases in terms of their structure and architecture, not in terms of their data. So if I were to spin up a Synapse dedicated SQL pool with 30 compute nodes, 60 compute nodes, then I would have 1 distribution or Azure SQL DB, right? We're going to start calling them distributions. I'm not going to call them Azure SQL DBs every time. Just know that when I say distribution, I'm not talking about a disk. I'm talking about a database behind the scenes. Okay. So then I'd have 1 per compute node. It's kind of like it would be saying, I'm going to set up 60 SQL Server instances with 1 database on each one. Making sure, of course, that those instances are on their own pizza box servers or virtual machines, right? They're not 60 different instances on the same node. Okay. And what's also really important here is that we always have an even number of distributions per compute node. Okay. Now, again, I'm talking compute nodes. There's always only 1 control node. And then our compute nodes go from 1 to 60. But as we start to step down, we go from 60 to 30. Anybody have a good idea as to why I can't have 35 compute nodes? Why can't I have 50? Why do I have to go from 30 to 60 and nothing in between? It's because I have to have an even number of distributions per compute node. Okay, and I can't do that when I always have 60 distributions. I can go from 2 per compute node down to 1, right? So basically, the size of our Synapse SQL pool in terms of compute nodes is always a relation to that, right? So go from 60 to 30, right? And then if I were to have 3 distributions per node, it'd be what, 20, right? And then we can start getting granular. And in fact, that's what I think why they chose 60 distributions, because with the lower end of the spectrum, you can have a single compute node, you can have 2 compute nodes, you can have 3 compute nodes, you can have 4 compute nodes, you can have 5 compute nodes. You see the granularity works really nice with 60 until you get higher. But if you're getting higher, those jumps become, that granularity isn't as important. All right. And then, like I said, there's the storage, right? So the storage is remote, which is basically the database. Okay, so the compute nodes, and then we got these databases. And the whole point of this is because if I want to scale up, all I have to do is detach the database from the compute node, spin up a new compute node, and move the ones that I detached over to the new compute node, right? But when I say move, all I'm really doing is detaching and attaching. I'm not actually moving data. I'm not having to go and split up my data from 20 distributions to 40. It's always 60. My data is always split 60 different ways. And so that allows me to scale up or down very easily because I don't have to copy data. I don't have to split it up. I don't have to merge it back together. Now, what you'll see along there with the compute nodes is you see SQL and DMS. So SQL is straight up a SQL engine. DMS is something called data movement services. So we've got the regular SQL engine running there, but we also have something called a data movement service, which is slowly becoming kind of phased out. But ultimately what that service does is it can move data from one node to another. Think of it as issuing SQL queries to grab data from one distribution and move it to another. That's data movement. And the reason that happens is because we have to split up our data 60 different ways. And there's 3 different ways that we can do that. Technically, there's 2 ways to split it up, but there's a third way that it can kind of work. And so if I need to join on something like product ID, and some of my product IDs on the second table don't exist in the distribution that I'm at, we have to move that data around. Okay, so that's one of the problems that is created with this architecture. I wouldn't necessarily say it's a problem, it's a consideration. And so we have to minimize that data movement because that's expensive, right? The whole point was we don't want to move data around from database to database. So the better that we can reduce that, the more performant our queries are going to be. But the data movement, oh, go ahead.
Oh, sorry, Jared. Can you control where these nodes are?
Yeah, I mean, are you talking about like the question is, can you control where these nodes are? And if that is that question revolving around like a region like East US 2 or Central US or something like that,
or even an availability zone within a region.
So the availability zone will be chosen based upon your based upon where your SQL pool is chosen. So yeah, like if I say I want to build my Synapse SQL pool here in Central US, then my availability zone is going to be that paired region. Whatever's paired with Central US, which I forget right now. I think it's probably East US. Okay. You don't get to pick where your DR region is or your availability region is. Those are paired, automatically paired all across Azure for most things, right? So it's not replication in the sense that you would typically set up like with an availability group or something like that. But ultimately, you are picking the region for this. And in the for the sake of speed and everything, they're going to be in the same region. In fact, it wouldn't put it past me that they're all going to be in the same rack or same data center because the whole point behind Synapse SQL Pool is speed, right? And so we want those things close together. Did that answer your question?
Yes, it does. Thank you.
Cool. All right. So there's my 60 distributions, right? And they will, like I said, evenly be split between the compute nodes. Okay. Now this right here, this is an example of a DW2000. So DW2000 is, remember like as we DTUs were like the thing for Azure SQL DB. So we've got a kind of similar type of thing for Synapse SQL pools. And basically, if you take the DW number and divide it by 500, that's how many compute nodes you'd have. Okay? So in this case, if I see a DW2000, then I have 4 compute nodes. Okay? So let's say I've got these 4 compute nodes, and I've got my 60 distributions. Okay? So that means I have 60 divided by 4 is, what is that, 12? So I've got 12 compute nodes, or 12 distributions per compute node. Is that right? No, 12 times 5, 61.
It's a 15.
15, yeah. Thank you. Jared can do math. Okay, so 15. Right, so I've got 15 of these things. Oh, and I've even got a diagram that could help me with that, kind of. Right, so our distributions are split up equally between our compute nodes. Now let's say I want to scale it up to a 5,000. Right, so what happens behind the scenes? Well, we shut down all the compute nodes, okay, which are basically shutting down the SQL DBs. We'll provision 6 more compute nodes, right? Because 5,000 divided by 500, right? Basically, we're adding 3,000, which is 6 compute nodes. So we're going to provision 6 more compute nodes. Then we will attach those SQL DBs appropriately. So instead of attaching all 15 to each compute node, we are now going to attach, let's see, what's 60 divided by 8? I forget. But anyway, well, so when we start this back up, we're just going to attach the appropriate distributions to the different compute nodes, right? So it'll be split up evenly. That's the whole point. But we didn't move anything. We didn't have to copy any data. We didn't have to split any data up. We didn't have to merge any data together, right? This was simply shutting down the databases and then provisioning more compute and then just attaching those databases directly to that new compute. That's it. Okay. So those 60 distributions, those compute nodes that hold those distributions, sit below the control node. So the control node houses a data movement service, which, like I said, is legacy, but it's still used for some things. But the idea is it's going to go away. The data movement service is also used for Polybase and some special kind of data movement operations. So I'm not going to go into it. But it also houses an Azure SQL database. Now, this control node database is just a shell, right? So it's basically schema and like architecture, right? Object definitions. It also houses statistics. So when I update my statistics, what it's going to do is it's going to aggregate the statistics from all the other distributions, right? Really quick, those of you who know about statistics know that we can have histograms with up to 200 buckets. That doesn't change here. So if I've got 60 nodes with 200 buckets each, I don't have 60 times 200 buckets in my histogram on my control node. I still only have 200. And so those have to be aggregated across. We also have TempDB on SSD local to the compute node or the control node, okay? And again, the whole point here is I issue my query to the control node. It knows about my compute nodes, and it's able to take that query and split it up as needed to go through. Okay. Any questions there? Okay. All right, so we go from our control node down to our compute nodes. Each compute node also contains an Azure SQL DB or more than one, right? Like I said, it's an even number per compute node. The number of DWUs divided by 500 equals the number of nodes. Now, that's not necessarily true for 100, 200, 300, 400, 500. Those are all a single node. So at that point, we're really just talking about compute power and memory and I/O stuff. Again, for dev unit testing purposes, not for performance testing. They all have an NVMe locally attached TempDB, right? So super fast TempDB, and they all have local cache. So again, you think of it just like a server, a SQL Server instance. Now here is a chart showing the differences from between our DWUs, memory, TempDB, and cache. Okay. And so what you'll see is our cache is very large. It has to be. The whole point of this thing is to be big and to handle large amounts of data. Okay. And it is fixed. There is no changing this in a dedicated SQL pool. There is no flexibility here. Okay. What you'll also tend to notice is that as the DWUs go up, our TempDB goes up. What we typically expect, though, is TempDB percent utilization to go down significantly. And that's because nobody should be using, even with all the data that they have, nobody should be using 117 terabytes of TempDB. If you are, we've got to talk about performance tuning your database. Okay. So are there any questions about that before we jump into table geometries? This is kind of really, this is going to start to explain how we split up our data and how do we get the performance that we want out of a dedicated SQL pool. No questions. All right, good. That means
I have another question.
Sure.
And, so I guess as everything spreads out, I would presume that the cost of this would also go up.
Yes. Yep. DWU's equal price. And a Synapse SQL pool is not one of our cheaper options, in all honesty.
Well, I wouldn't think so.
Right. Nor should anybody, right? I mean, it's a lot of compute, right? If I go back here, let's see, can I go back? Yeah. Right? I mean, we're not talking about peanuts here, right? We're talking about the peanut, several of the peanuts, right? 90 terabytes of cache, right? 18,000 gigabytes, right? That's not 18 gigabytes. That's 18,000 gigabytes.
Hey, Jared, I have a question.
Yes.
Can you hear me?
Yep, I can hear you.
How are you? It's Dave Keegan.
Good. Hey, Dave, how are you?
Good. Is there anybody doing that? Is there anybody using the Synapse analytics tools at that scale?
Yes.
Yeah. Can you
Yep.
tell us who and
I cannot.
what kind of company are they? What kind of processing are they doing?
There are several.
Yeah.
And so certainly I think I'm okay with saying, actually, this is even a guess, right? So I'm guessing just kind of things that I've heard. Fast-paced things like, think of the gaming industry.
Okay.
Think of people who need to crunch massive amounts of data in a very short amount of time. And really, that's what we're talking about here. The reason that this is out here is for computational purposes over massive amounts of data. We are not selecting singleton rows. We are not booking airplane tickets. We are not buying products, right? This is going out and saying over the past 30 years, which products have been our biggest sellers and which will be the biggest sellers based on yesterday's data combined with the last 30 days, combined with the last 60 days, right? I mean, this is predictive analytics. This is machine learning. This is large scale analytics against, for the most part, our entire data set. I'm not using this for small subsets of my large data warehouse.
Right. No, that makes sense. I guess, yeah, at some point, I'd be interested in having you address the issue of getting all that data ingested.
Sure.
How does
Well, we'll
that
talk a
happen?
little. We'll talk a little bit about that, right? Because certainly it's a typical ELT ETL paradigm. Okay. So let's talk, and I'll reference some of that as we talk about table geometries and indexes. So for instance, we have 3 different table geometries. Okay. Some people call this like these distributions. The thing is, one of them isn't really distributed, but it kind of is, but it's not, but it is. So we'll talk about that. But hash distributed. Okay, so what is hash distributed? A hash distributed. So when you create a table now in a dedicated SQL pool, it is always going to be one of these 3 things. There's no way around it. Okay. And if you don't define what type of table it is, what the distribution is, it will be a round robin. But let's start with the hash distributed. So a hash distributed means that when we insert data, it's routed to the proper distribution based on a hash function. Now, you don't get to choose your hash function. You don't get to pick from several, right? You don't create it. The hash function is built into the dedicated SQL pool. It is some type of super secret sauce. I don't know what it is. Maybe I could find out if I wanted to, but I don't, because it's above my pay grade, and quite frankly, it's irrelevant. But what it does is it takes the value of the column that's chosen and it applies this function to it. And based on the output of that function, it determines which distribution that data goes to. Now, those of you that know anything about hash functions know that number one, it's usually deterministic, and in this case, it is. The same value will always hash to the exact same distribution. But something to note about that is that when I say the same value, I mean the same value and same data type. Meaning that an integer of 1 and a tiny integer of 1 and a small integer of 1 and a big int of 1 are fundamentally different values as far as the hash distribution function is concerned. Okay? Because they're different binary encoding. They're different sizes. And because of that, the hash distribution function, I don't know that it uses a different function based off of data types, but because of that, they will hash differently. The other thing about this is the hash distribution function does not guarantee uniqueness, meaning that it's possible that out of 60 different values, and in fact, from what I understand, it's not just possible, it's likely that if you have 60 unique values in a hash distributed column, it will not hash out to all 60 distributions, right? We may have 2 or even 3 or 4 empty distributions by the time all is said and done with those 60 values. Okay. So we need to pick a column for our hash distributed table that is usually relatively unique so that we get a good spread of the data. Okay. And is also relatively evenly distributed, right? This is different than partitioning. I've heard of some people reference these distributions as partitions. They are not partitions, because when we partition, we try to pick a partition column to when I query it, I can limit the number of partitions that I query, right? I'm trying to reduce the number of partitions I hit. If I have 60 workers sitting down on a conveyor belt and only 30 of them are doing work, I'm paying for 30 other people to not do anything. And that's not good. And that mentality needs to be brought into this MPP architecture. So for instance, picking a date column as a hash distributed column or as the column for my hash distribution is typically a very poor choice. In fact, I had people that picked date and they had, I think, 5 or 10 years of data. And 2 distributions were empty, completely empty. with billions of rows of data. Why? 'Cause, I don't know, for some reason that date did not hash to all 60 distributions. What that also means is that all the data that I load for a particular day gets hammered into a single distribution, right? And so that's problematic. Now, this particular customer, that was a date time column. So I said, well, the problem is you guys aren't storing the time information. If you were, then it becomes a really great hash distributed column because almost every single row that comes in has a different value. And so we evenly distribute those rows across all the distributions. Okay, but there are other considerations to take in mind. What we want typically to do with our hash distribution is not only make sure that they're evenly distributed and that they're not really skewed, but we need to pick the columns that are used for things like joins. Because as I told you briefly earlier, and we'll talk more about this with data movement, is if I'm joining on a column where the data resides in different distributions for that column, or for those rows because of the column chosen, then I have to move either some rows from table B or some rows from table A. Okay, we'll show an example of this later. Hash distributed tables are typically our final resting place for fact tables, right? We're talking about a data warehouse here. So we're typically talking about some type of star or snowflake schema. Right, so a hash distributed table is typically, in general, what we use for our fact tables. Round robin, on the other hand, is what we typically use for our staging tables or when we can't pick a good hash distribution column. Okay, so what is round robin? That's our default, and all that means is that the incoming inserted data, right, is distributed evenly across all the distributions. Right? It's round robin. So it just goes distribution. It technically it doesn't go to 1, 2, 3, 4, 5, 6, 7, and then get to 60 and go back. That's not the technical implementation, but for all intents and purposes, logically, that's what it does. Right? So it guarantees an evenly distribution distribution of our data. Okay, and again, it's commonly used for staging because typically to get the data in from point A to point B, our data lake, our streaming service, whatever that may be, we want to get it in to the MPP platform as fast as possible, and this is the fastest way. Once it's in there, we can now use the MPP architecture, the compute nodes, to move it around, to transform it, to get it to its final resting place for querying. Okay. And then the last type of table geometry is a replicated table. So a replicated table essentially starts out as a round robin table, but when it's first queried, it will build a copy of all the data on each compute node so that it's accessible by all distributions. This is typically our dimension tables because we join our fact tables usually not to other fact tables, but to dimensions. And so it makes more sense for those dimensions to be everywhere so that we don't have any data movement. They're also typically smaller and slowly changing or static. Because remember I said, once we load data into these, they come in as round robin to a replicated. Only after that table is queried does it build a copy of that replicated table cache. Okay? And that in and of itself can be an expensive operation. When does it do that? If the data changes. Anytime the data changes, it invalidates the current replicated table cache. Now, if it's really, really small, that may not be a big deal. But if it's large and it has to rebuild and that takes a long time, you may be better off just leaving it as round robin and not even having it replicated. Typically, we say that this works best for data, like I said, that's static or slowly changing and less than 2 gigabytes. Again, that's just a general rule of thumb. Because if it's greater than 2 gigabytes, but that data is never changing, like almost never, so we never have to rebuild that replicated table, then it's not very impactful, right? But even a small replicated table that is frequently changing, something like an OLTP to style, can be problematic. Okay. The other time we usually say 2 gigabytes. We'll also sometimes say like 100 more than 1,000,000 rows, or I'm sorry, less than 1,000,000 rows. As soon as we get to be more than 1,000,000 rows, they can become problematic. But again, your mileage may vary there. Any questions about table geometries? Okay. Something that's very important to understand is these table geometries are independent. They are mutually exclusive from indexes. Okay, because we're going to talk about indexes now. Heaps work the same, right? Clustered and non-clustered indexes work the same. But there's 60 of them, right, for each table. Column store indexes work the same mostly. So let's talk about that. The default in an Azure SQL, a Synapse SQL pool is a column store index. So if you don't change that, which you probably should for your replicated tables that have less than 1,000,000 rows, and really, as you'll see in a Synapse SQL pool here, if you have less than 30 million rows, you probably shouldn't need a column store index unless you're planning on growing that relatively quickly. Okay. But as we've talked about in column store discussions, the column store works best with at least 1,000,000 rows, but we have 60 of these tables. We have 60 column store indexes for every table that we create because we have 60 databases. So 60 million is optimal, not just per table, like not just to sit there. When we load these, right? We're not talking small potatoes here, people. We're not talking load 10 rows at a time or 100 rows at a time or 100,000 at a time. We're talking about optimally batching 60 million rows in a single insert. Okay, that's optimal. Not always realistic. We're okay with 30 million because what does that do? 30 million gives you approximately 500,000 per column store, which, if you've heard my column store talk, that is acceptable, right? Getting lower than that can be problematic. Okay. Another difference is that when you reorganize a column store index in SQL Server or Azure SQL DB, it does a lot. A reorg will compress, or it will close open row groups. It will also defragment. It will try to reorganize and recompress your row groups. It basically does everything. Like there's pretty much no need to do a rebuild for column store indexes in Azure SQL DB or Azure or SQL Server. That is not the case in a dedicated SQL pool. It follows the old original column store defrag stuff. What does that mean? A reorg does one and only one thing. It closes open row groups. That's it. I'm sorry. Yeah. Closes open row groups. Okay. If you need to do more than that, you need to do a rebuild. And so if you think about an ETL process, we're actually going to start to build a lot of this index maintenance into our ETL process. Load data, rebuild index. Load data, update statistics. Okay. Not every Sunday at midnight we do index maintenance. That's not what we do here. The paradigm is different. Okay. Now, something just to kind of note, even though we're not going to go into detail of this, adaptive cache is a feature of our dedicated SQL pool, An adaptive cache is kind of works like, think of it like our buffer cache in SQL Server, our page life expectancy. The difference is it holds those uncompressed blobs from the column store, and it's faster. It's like NVMe. It's cache. Okay, so it's super fast, but it's only for our column store. So there are cases where we don't have these 30 million rows or 60 million rows, where column store still works and helps because of the fact that we're caching everything. Even though it's not optimal in terms of row group size or things like that, we added this feature to kind of help with that, because not everybody is going to have tables that are loading batches of 60 million rows at a time. Right? And there might be some fact tables that are smaller but still need to be used in the same way. Okay. The other thing to note about our clustered and non-clustered indexes, so our row store stuff, everything is page compressed. You can't turn it off. You can't choose between page and row. Everything that is row store is page compressed. Okay. Any questions about our indexes? Okay. So taking those table geometries and potentially our indexes to a certain degree into consideration, we need to now talk about data movement. Okay, so when data doesn't exist for an operation that we're doing in the same database or in the same distribution, right? It has to move the data from one distribution to another, right? This is the primary cause of performance issues in a Synapse SQL pool. So it's really important to really think about, how am I using this table? What is the geometry I'm going to use for it? How are people going to query this table once it's all said and done? And it's not uncommon. I wouldn't say it's common, but it's not uncommon to see duplicate data stored in different ways in a Synapse SQL pool. The same table basically being copied, so I shouldn't say it's the same table, but two different tables containing the exact same data, but on a different hash distribution key to satisfy different needs of their users. Okay. But there's other things that we can do here too. We can do materialized views. It's not the same, it's similar to an indexed view in SQL Server, but it's much easier to create. It's like create materialized view, which is basically a copy of your table doing whatever you want it to do. Typically, it's done in aggregations and stuff like that, and it's automatically updated when you insert into the table. So that when I request a report, right, I can use that view instead of the table. And that view can be distributed on a different column. So maybe I'm not actually creating two separate tables. I'm creating one table that's hash distributed on my most commonly used column for joins. But there's a couple of these crazy queries people use, and they have to use a different column, and we're seeing too much data movement for that query. So I create a view on that table with a different distribution to satisfy that other query. That's popular. But what's probably more popular is more aggregated, like pre-aggregated views that just maintain those aggregations as data comes in. And that reduces data movement as well. But let's kind of try to understand this a little bit more. So let's think about our fact order detail and our fact order header. Now, those of you that are familiar with our AdventureWorks sample databases or wide world importers know about these tables, right? The order header has a header ID, and then that header ID is a foreign key in the order detail. So we can take all the order details and group them together under a particular header, right? So how are we joining these tables? We're almost always going to be joining these tables, and we're almost always going to be joining them on the header ID, right? The order header ID. Now, it's a little bit against our typical design paradigms or patterns, right? For a SQL for a data warehouse, because in most cases I would have these things denormalized and I wouldn't be joining them. But it does work well for the case of this demonstration, and that is that if I distribute my fact order header table on header ID, right, the typical clustered index key, which again is different than the hash distribution key, right? They're two separate things, so they don't have to be the same. So my clustered key usually, and in a column store index, it's irrelevant anyway. But let's just, so we've got our fact order header, let's say that is hash distributed on header ID. And then we've got our order detail ID table, which is hash distributed on order or detail ID. Okay, which just kind of goes with our typical relational design. The problem is when I look for orders for header ID 1, they have different detail IDs, right? Like detail ID 1, detail ID 2, detail ID 3. And so they're all over the place. So when I try to join within my same Azure SQL DB, within my same distribution, the data isn't there. It's on other distributions. So I have to get it. I have to get it over to distribution, let's say 1, right? Because, or more than, maybe I have to get everything from distribution 1 over to the other distributions. So it just depends. The optimizer will figure that out for me. That's what the control node does, in fact. Okay. So really, how does it do that? It actually, the control node will create a temp table and select the data it needs from the different distributions and pull them from all those distributions onto a single distribution into a temp table so it can be joined, right? But we don't want to do that. That's expensive. So really, in this case, what I should have done is hash distributed on, in my detail table, I still would have picked a hash distribution key for my header ID. Would have been a better choice because there's no good reason for me to query the detail table without joining to the header table, right? Now I'm sure you could come up with some reasons, but in general, I wouldn't, right? If I am querying the order detail table, then I'm querying it on its own. And I'd be grouping by header ID or something, right? So that's data movement. We try to minimize it, right? Here we've got 1, 2, and 3 sitting in this bucket, but because this one's distributed on a different column, 1, 2, and 3 are in different places for my header ID. It's my detail the detail ID, maybe 1, 2, and 3 are still in this bucket, but we're not joining on detail ID. We're joining on header ID. So that's spread across these other distributions. Okay. So that's expensive. So that's what we try to minimize. And we do that with a proper hash distribution key and then replicated dimension tables. Where we see the biggest problems is when people are joining fact tables together. Because typically if they're two different fact tables, they're hash distributed on different columns that are not necessarily relating the two tables. So be careful about that. There's kind of my fake distribution now, so now I can join. Are there any questions? Maybe a lot. I mean, this is Synapse dedicated SQL pool MPP architecture in an hour. Any more questions? Did I do so good that nobody has any questions about what's going on?
I have a question.
Okay.
You were mentioning about the indexing.
Mm-hmm.
Give me your spin on I guess, maintenance. Or
Right.
these, I mean, I assume because it's, it's a, I guess this is a platform as a service. A lot of the maintenance is handled in the background, but it sounds to me like you're still going to be up against reindexing.
Yeah. So
I could put a laundry list of, all the maintenance jobs and procedures that you may have to do, at least coming from a lot of people here tonight, from just SQL Server.
right.
What can you expect when you're processing this kind of, this kind of sizes that we're talking about here?
Sure. Sure. So let's talk about that. So number one, what are our main maintenance tasks, right? Backups, index maintenance, and statistics maintenance, right? That's pretty much it. All right. So let's take backups out of the equation because it's platform as a service. And we do have, snapshots. You can take manual backups and stuff like that, but most people don't take manual backups unless they're doing some type of big change. Okay. All right, so let's take backups out of the equation. Now we talk about indexes and statistics, and no, neither one of those are automatically handled for you. In fact, statistics, though automatically created in a Synapse SQL pool, it's frowned upon to do so in a production level. In fact, what we actually provide on our documentation is a script that will literally go through and create a statistic for every single column in your entire database. And so some people do that. Here's the other thing. Statistics are not auto-updated in a Synapse SQL pool. They are the distributions. The distributions are just Azure SQL DBs, so they're auto-created, auto-updated. But at the control node, which is really where I care about this, they are not automatically updated, which means you must update them basically every time you change data, which is why your maintenance becomes a part of your ETL process. There's no reason to do maintenance unless data changes, and data change, it doesn't typically change in a data warehouse except for at the ETL or ELT process, right?
Right.
Now, am I going to say that nobody is inserting a row at a time or 100 rows at a time? No, there's people out there doing that. But then that creates issues and they have to figure out how to deal with it, right? I had a customer, now this was on SQL Server, but I could extrapolate it up to a Synapse SQL pool. And that is that they were frequently updating and inserting rows throughout the course of a day in this particular table. But at the end of the day, once the markets closed, that data stopped changing. And so they were running into problems in their clustered column stores because of the fact that they kept doing updates and deletes, right? Which column store does not handle very well.
Right.
Okay. So what they did was they ended up creating a row store table for these inserts, updates, and deletes, and then a clustered column store table, and then they created a view that did a union all against both of them. And so the queries, the reports, the analytics that they were doing would basically query both tables through the view. So they were just hitting the view, right? But they were maintaining their inserts, updates, and deletes and stuff like that there. Then at the end of the night or at the end of the day, they'd run a process that moved all that data into the column store. And after they were done with that, they would rebuild their indexes and such. Okay. So the same paradigm kind of applies here. You have to get sometimes creative depending on the use case. But in general, data doesn't change unless you're loading it into the table and transforming it, which means as a part of that job, whether it's Python, Spark Notebook, or Azure Data Factory, whatever, the last step in that process would be to rebuild your indexes and update your statistics.
That sounds like it could be a killer when you're talking about 60 million rows, every whatever, a minute every second, isn't that gonna eventually come back and haunt you?
Well, so I would say that most people in these paradigms are not loading 60 million rows in a second or per minute. We're talking about maybe hourly, but probably most commonly, we're talking about daily loads, right? People offload stuff into the data lake at the end of the day from different locations, and they process it all at once. Now, think about this. So let's say you're rebuilding an index on 60 million rows. Really, what you're rebuilding is 60 indexes on 1 million rows, right? Which is theoretically in a column store only a single row group. That's nothing. That'll take seconds.
Okay.
Right? And so because of the high level of compression, because of the heavy reliance on column store, these things shouldn't take too long. And there's other things that people do. So for instance, rebuilding a clustered column store index takes longer and more resources than doing something called a CTAS operation. We talk about a lot in a dedicated SQL pool, which is create table as select. So to rebuild that column store, we will typically dump all our data into the column store and then do a create table as select and then rename them after it's done. And that's our rebuild. In fact, in a Synapse SQL pool, something else I didn't mention, you can actually create an ordered clustered index, which helps with row group elimination. It's essentially partitioning, but you don't want to partition in a SQL pool unless you really have to, because now you need at least 60 million rows per partition.
Yeah.
Hey, Jared.
Right. Yeah.
Yeah, Jared, I think we have another question.
Okay.
Tom, did you have a question?
I do. Hey, Jared.
Hey, how's it going, Tom?
Good. Hey, I have a question about table geometries.
Okay.
Specifically for a dimensional table that has less than 2 gigabytes of data. I mean, that's hardly anything, right?
Mm-hmm.
How much of a performance benefit are you really going to see on a table that has less than 2 gigabytes of data by switching it to a maybe my question doesn't make any sense. These table geometries here, do you choose these table geometries, or does the Synapse magic do it for you?
No, you choose them.
Okay. Okay.
There is a default, but you choose them. And typically,
Okay. So
your replicated table will be, and this is just in general, will be a row store clustered with maybe some non-clustered indexes, but primarily, like think of a date dimension, right? You've got some type of date ID or something like that. It's going to be a clustered row store replicated table. It would not be column store, and it wouldn't follow one of the other two geometries.
Gotcha. So so what my question is then is, how much performance gain am I really going to see from moving a table from round robin to replicated if it has less than two gigabytes in it?
Depending on how many queries are hitting that table, it could be relatively significant. I mean,
Okay.
2 gigabytes. So first of all, just remember 2 gigabytes of compressed data is
Okay, so it's
is
probably
a lot of data.
It's probably 10. It's probably 10 to 1. So let's go with Okay.
And then well, not necessarily in a row store, right? Because we're not talking about column store. So
Okay.
compression might be 2 or 3 to 1.
Oh,
But let's talk about that, right? So what happens, and this gets into kind of some of the details, right, about what happens with a replicated table. When the data changes and it's replicated, right, I have to do a replicated table cache rebuild. And so the first query that hits that invalidated replicated table will initiate the rebuild. All of the other queries coming in will treat that table as a round robin until it's rebuilt. And that means data movement. So instead of moving the data once, we're moving it a lot. Now think of something like a date dimension. I mean, that's used on probably almost every single query that hits the Synapse SQL pool. So to have to do that round robin and that data movement every single time for every single query is expensive. whereas we do it once, right? And then it's cached.
Okay, that helps. Thanks. So this is a kind of an awkward question, but when does it make sense to just simply up the DWUs on your database? When is it better to just take the easy way out and up the DWUs on your database?
That's a good question. So,
because that, 9 times out of 10 is what I see customers doing. And it's the magic of the cloud, really.
Right.
I mean, they should be tuning and they should be doing all this, but it's so easy to, take 5 minutes and up the DWUs instead of, paying somebody whatever for however many hours to figure this stuff out,
Right. Yeah, and that's a good question. So typically, it's hard to say,
Yeah.
but a lot of it will revolve around concurrency limits as well. So for those of you who don't know, there is a finite amount of concurrency, meaning that the number of queries that can run at any one particular time on a Synapse SQL pool.
Right. Yeah.
And that increases as the size goes up. Now, of course, if you can make those queries run faster, then concurrency becomes less of an issue because you're spending less time waiting for your turn to execute your query, right?
Yeah.
So that's one piece. But there's two metrics you can look at in the portal, and I think these are just regular metrics. I don't even think you need special log analytics for this, but that would be queued queries, number one. So am I waiting? Do I have people waiting to do work? And then the second would be looking at my CPU and IO utilization relative to my, the total resources on the server, the total DWUs. So typically we see like as I approach my utilization, getting close to DWUs, like to hitting 100% utilization, it's usually tracking with CPU, almost exactly. And so when I see that hitting 100% for an extended amount of time, and when I say extended amount of time, this is something different from SQL Server. Sitting at 100% for 5, 10, even 15 minutes is not a problem in a dedicated SQL pool, unless we have excessive amount of queuing. But we're paying for these resources. We want to use them, and it will use 100% if you can. If you allow a particular user to do it, it'll do it, and that's okay, right? Because that's what it's designed to do. So if I see prolonged periods of 100% utilization, that's when I start to say, okay, we need to size up, right? We don't have queued queries, but we have 100% utilization. Or we have a lot of queued queries and 100% utilization, and that's a problem for my end user. But if I have a lot of queued queries and we're not using all the resources, then it's time to think about optimizing, workload group management and maybe even some of the queries as opposed to sizing up.
Yeah, I recently ran into a 30,000 DWU Synapse that was experiencing, a lot of these metrics were maxed out. Anyway, fortunately, I wasn't tasked with figuring out why. But I have run into, somebody had a question, well, who's using this? I mean, there are some, think of like the biggest pharmaceutical companies are using these, for example. So anyway, I am seeing inefficiencies at these higher levels. So there does come a time when even turning up the dial is there's an end to it.
And I would be willing to bet a good amount of money that it was one of two things, and I would put most of my money on the fact that they were not updating their statistics because they just assumed that it automatically updated it.
Yeah.
And the second thing that I would say would, be a poor hash distribution key or a bad design. But 90% of the customers that I go to with performance issues don't understand that statistics are not updated automatically, and and they're not maintaining them as part of their ETL process. And that typically causes excessive amounts of data movement, which just blows their IO out of the water, and that's what's bringing them up to 100%.
Yeah, fascinating.
Mm-hmm.
So, Jared, I have a question, a follow-up question to that. So where do you see this? Is this Azure Monitor? Where do you go to find?
Yeah, those simple metrics you can see in Azure Monitor, but for more kind of advanced stuff, what I suggest people do is actually enable log analytics. Now, there's a way to do that because it can become very expensive if you're logging everything that's available to log. However, we do have a public repo that is managed by some customer engineers. Let me go here and see if I can drop this out there. So this is, this is for people to check out. It's called the Azure Synapse Toolbox. I'll drop that over here. And it walks through how to set up log analytics. It tells you how you can deploy some of these workbooks and dashboards, and they can feed off of some of the log analytics data as well as the monitor data. But your basic stuff is going to be in the monitor, Azure Monitor.
Okay.
Does that answer your question?
Yeah, that's a good route to go.
Any other questions? All right, cool. Well, thank you everybody for joining the discussion tonight. Thank you on behalf of myself and Ross, although I'm sure Ross can say thank you as well, but also just thank you from myself for attending and asking some great questions.
Yeah, and thanks for presenting, Jared.
Very welcome.
It was a great presentation, great discussion. Next month, as I had said earlier, that Alpa will be joining us, and she'll be talking about Azure Data Factory. So
all right,
that's April 14th.
Cool. Everybody make sure to join us next month.
Yes, absolutely. So thank you all for attending, and have a good night and the rest of the month, and we'll see you next month.
Great. Thanks. And we'll
Thank you.
stop the recording. All right.